Welcome, everyone. Today, we are exploring a massive leap forward in Elixir's performance, a 400-fold acceleration of its type system. In this session, we will conduct an analytical teardown of how the implementation of lazy binary decision diagrams, or BDDs, mathematically optimize set-theoretic types within Elixir version 1.20. To put the real-world impact into perspective, these optimizations have reduced type-checking computation from 10 full seconds down to just 25 milliseconds. This shift represents a fundamental improvement in the developer experience, transforming a significant bottleneck into a near-instantaneous process. To achieve complete type inference in Elixir, the system must be capable of representing complex set-theoretic types. However, using disjunctive normal forms, or DNFs, results in what we call the flattening flaw. This approach forces an immediate flattening of these complex structures, as illustrated by the tangled baseline on the left. The primary symptom of this flaw is a Cartesian explosion. When calculating intersections of unions, for example, combining foo or bar and baz or bat, the system generates massive Cartesian products. Similarly, unions of differences trigger exponential expansion. This computational overhead severely impacts performance, ultimately halting system speed and making the use of traditional DNFs impractical for this scale of type inference. The structural anatomy of a lazy BDD is defined by 4 core components that facilitate sophisticated type representation. At the top left, we have the literal, represented by A, which signifies the base type, such as tuple elements. This is paired with the constrained component, C, which is inextricably tied to the literal to define specific constraints. In the lower half, the uncertain component, U, manages unresolved types, while the dual component, D, is dedicated to negated representations. The power of this structure lies in its ability to maintain set-theoretic operations, specifically unions, intersections, and negations, as a tree at arbitrary depths. By utilizing this hierarchical approach, lazy BDDs entirely avoid the exponential flattening often seen in disjunctive normal forms, or DNFs, allowing for a much more efficient and scalable representation of complex logic. Let's examine 3 groundbreaking algorithmic insights that redefine how we approach complex computations. The first is the paradox of eager evaluation, where we challenge the standard reliance on pure laziness by forcing early literal intersections to improve overall efficiency. Second is disjoint literal elimination, a technique that allows us to bypass tree expansion entirely when computing subset differences, specifically in cases where D2 evaluates to bottom. Finally, we have negated component decomposition. This insight focuses on transforming complex negations into reusable eager intersections, which is particularly effective when D2 is not bottom. These 3 strategies work in tandem to significantly optimize our algorithmic performance. Our first key insight involves strategically violating laziness. While lazy evaluation is generally optimal for handling type unions and differences, it becomes a significant liability when dealing with intersections. To address this, Elixir employs a specific mechanism. It computes the intersection between literal types immediately, rather than deferring the calculation. This eager evaluation enables aggressive pruning. If the intersection of 2 literals is found to be empty, the entire node is instantly eliminated. This recursive evaluation clears out subsequent empty subtrees, preventing the massive tree growth shown at the top of the slide. As the performance metrics demonstrate, this approach reduced computation time from 10 seconds down to just 25 milliseconds, effectively collapsing a complex tree structure into a single, simplified node. Boundary constraints distinguish between closed and open maps to optimize type-checking performance. Closed maps, illustrated on the left, utilize strictly defined keys. Because the structure is fixed, intersecting these maps often results in empty types. This behavior makes eager literal intersections a highly effective strategy for pruning, allowing the system to quickly narrow down valid types. On the right, we have open maps, which typically arise from pattern matching against maps with unverified keys. Since the full set of keys is unknown, intersecting these types rarely allows for the elimination of entries. Instead, it can trigger expensive Cartesian products, significantly slowing down analysis. Consequently, the Elixir implementation selectively targets closed maps for these optimizations to prevent massive performance regressions. Insight 2 focuses on disjoint literal elimination during Phase 1. The core goal is to optimize the operation B1 minus B2, rewritten as B1 and not B2, specifically for cases where D2 is bottom and contains no negated component. To manage this difference effectively, the first BDD, B1, is bifurcated. This allows us to isolate the literal A1 and its constrained component C1 from the remaining uncertain parts, represented here as B1 underscore no C1. Following this isolation, we proceed to step 2, distribution. Here, the expression is expanded to include the negated B2 term, resulting in A1 and C1 and not B2. This targeted approach enables more efficient processing of the logical difference within the BDD structure. Moving forward with the process of distributing negation across BDD subtrees, we begin with step 3, substitution. Starting from our initial expression, A1 and C1 and not B2, we substitute B2 with its expanded definition. Since D2 is the bottom node, B2 simplifies to the expression A2 and C2 or U2. This substitution results in the logical statement A1 and C1 and not quantity A2 and C2 or U2. Next, in step 4, we perform the distribution. Here, the not operator is distributed across the terms within the parentheses. By applying De Morgan's law, the internal OR becomes an and the negation is applied to both subexpressions. This allows us to drop the outer parentheses, resulting in the final form, A1 and C1 and not quantity A2 and C2 or U2. The core optimization we are discussing is the concept of vanishing subtrees. Consider the logical expression A1 and C1 and not A2 and C2 and not U2. In step 5, we identify a critical opportunity for simplification. If the literals A1 and A2 are perfectly disjoint, meaning they have an empty intersection, then the subexpression A2 and C2 is merely a subset of A2. Since it shares zero overlap with A1, evaluating A1 and not A2 and C2 results exactly in A1. Consequently, as indicated by the red cross, that entire section of the expression vanishes. Moving to step 6, the resulting right-hand side is rebuilt into standard BDD format. This optimization is highly efficient because it allows the tree to be constructed without ever needing to add A2, significantly streamlining the overall process. Insight 3 focuses on negated component decomposition. When D2 is not bottom, B2 is shown to contain a negated component, specifically the expression not A2 and D2. This decomposition breaks B2 down into B2 underscore no D2 and this specific logical component. In a set difference operation, represented as B1 minus B2, this negation effectively becomes an intersection. By distributing the negation, the mathematical expression transforms into B1 intersected with the negation of B2 underscore no D2 and further intersected with the result of A2 or not D2. This transformation allows for a more granular analysis of how these components interact within the overall logic of the operation. Algorithmic recycling focuses on the efficient reuse of eager logic across different phases of computation. As illustrated in the cycle, we start with components decomposed from Insight 3, which feeds directly into our optimization strategies. In the bottom optimization phase, the final simplification relies on B2 no D2. This is defined so its D2 component is effectively bottom, allowing the system to reuse the phase 1 optimization without redundant processing. Moving to the eager intersection, we see that distributing B1 results in the computation of both B1 and A2. This step is significant because it utilizes the exact eager literal logic already built, minimizing overhead. By recycling these logic structures, the system maintains high performance through the strategic reuse of previously established literal logic and optimizations. Let's examine the pragmatic compromise identified during the peer review process. When we look at the implementation reality, we find that despite the mathematical validity of Insight 3, the Elixir team chose to omit this specific optimization from the current version of the compiler. This decision stems from an unstated assumption that code patterns involving negations on the right-hand side are statistically uncommon in typical Elixir development. By making this choice, the framework deliberately sacrifices theoretical completeness in favor of a more focused, pragmatic scope that addresses the most frequent use cases. Moving to the evaluation of the unstated assumption, we have assigned it a criticality score of 7 out of 10. While standard application code rarely employs RHS negations, library developers and macro authors pushing the boundaries of type inference will frequently encounter this path. The likelihood of failure is categorized as moderate. As developers adapt to v1.2 type checking, the use of complex set-theoretic abstractions will inevitably grow. Should this assumption prove false, the consequences are significant. Advanced difference operations will hit a sudden performance cliff, resulting in a fallback to unoptimized BDD expansion. The Elixir BDD optimization routing framework serves as a master logic map that dictates our type system's overall performance. The routing process begins by identifying the operation type. Under path A, which handles intersections within an interval, the framework evaluates whether the map is closed. A closed map triggers an eager literal intersection, whereas an open map results in a lazy BDD execution. Alternatively, path B manages differences within an interval by determining if D2 represents the bottom element. If so, the system applies disjoint literal elimination. Otherwise, it defaults to standard, unoptimized execution. By directing traffic through these specific logical pathways, we are able to trigger 25 millisecond accelerated optimizations, ensuring peak efficiency for the language's type system. Pragmatism over algorithmic purity is a core principle for building performant, resilient systems. Elixir's massive leap from a 10-second execution time down to 25 milliseconds was not the result of chasing flawless mathematical symmetry. Instead, it was achieved through the intentional, strategic violation of abstraction rules when theory met the friction of real-world constraints. As the diagram illustrates, maintaining the integrity of our core components requires a nuanced balance. Ultimately, even the most beautiful abstractions need localized, precise pragmatism to survive the rigors of production.